without 5G. Right now, 5G like is talking, deployment, lots of things. He's one of the pioneers to promote that. So for your information, he is a professor in electronic engineering. This royal recognition was awarded to mark the Queen's Diamond Jubilee. Rahim Tafazolli has been a professor of mobile and satellite communications at the University of Surrey since April 2000, the director of Institute of Communication Systems since January 2010, and the founder and director of the 5G Innovation Center since 2012. This is the first dedicated center on 5G research and innovation. He has published more than 500 research papers. In 2011, he was appointed as a fellow of the Wireless World Research Forum in recognition of his personal contributions to the wireless world, as well as heading one of Europe's leading research groups. He was also awarded the KIA Laureate Award 2015 for his contribution to communication technology. Please welcome Rahim.
Okay, thanks, Richard. Thanks for kind words and introduction. What I would like to discuss with you is what is after 5G. That's effectively. And purposely, I've chosen this title of New Internet because, and I'm not calling it 6G or 7G or whatever it is, because whenever we do a G, the standards always focus on the radio side. Whereas the most important aspects of after 4G is the core network and the fixed part of the network, which is to deliver all these challenging technical requirements in terms of the latency, in terms of reliability, in terms of bandwidth, and etc. So for this reason, I'm not gonna in any of my talks talk about 6G or 7G or whatever G is, and to mainly focus the message, what we mean by the revolution that we need or evolution we need into a system that can meet the requirements in 2030, 2040 and above, and later than that. So to start with, just a very quick overview of what 5G Innovation Center is and what we have done. I think it is not completely unrelated. The 5G Innovation Center was established in 2012. When we talked about 5G, many people from even industry, they said to me, I'm crazy, because 4G was not even deployed in UK. Not even frequency bands were deployed, was allocated in UK. And after we started this one, and many companies joined the initiative, now is probably the biggest innovation center dedicated to 5G technology. And the research we are doing is not only the wireless side, because many people have this connotation of 5G means only mobile broadband or wireless side, but we do end-to-end aspects of the 5G. So the membership started with the 8 founding members, which Huawei was one of the founding members with the, originally, and is more than 26 international companies are the members, representing different organizations in the ecosystem. As you see, we have regulators, we have vendors, we have all the UK mobile operators that are members. BBC, it's a broadcasting, is a member. McLaren for, Formula One, McLaren, etc. As well as the Ofcom, because we need to carry the regulators with us, because they will decide on the policies of the future. So what is our job? We being an academic institute, our industrial partners, they said to us, don't worry about backward compatibility, all that sort of things. They said, what is the art of possibility? What can you do? How can we push the technology and the science to the limit? Tell us that. We want the fact, we want the truth. On the radio side as well as on the fixed side, which is a fantastic mission given to an academic institute. So we have open hand and we can explore all the possibilities that possible. So 5G, many people, as I said, wrongly, despite the fact for the last 6 years we've been saying what 5G is, they think that it is mobile broadband communication system. It's more than that. I normally in my talks say it is a special generation and should not be compared to 4G or previous generation systems, because it's not only about communications between people, but also it is about automation. Automation connecting many objects. Perhaps we connect more objects and machines together than human beings. And that automation makes 5G very different. Obviously, automation, connecting robots, for example, or a car or whatever, different size, they don't understand delay. They don't understand latency like human beings do. So for this, reliability in terms of guaranteed delay and wireless connectivity, of course, is extremely important side. So another aspect of the 5G is, as I mentioned, is to provide one network technology. One network technology, not one network, but one network technology that can support all this vertical industry. It's never been done before, not in 4G or previous generation systems. So obviously the network has to be extremely programmable with a different degree of quality of service, quality of experience, different degree of resilience, different degrees of latency, all in one network technology. And something else that we've never done previous generation is we never designed any telecom networks to guarantee. I think the word is guarantee. Somebody mentioned this morning, but guaranteeing the delay is not necessarily just low delay. How can we guarantee 99.99% of the time the delay is 10 milliseconds or 20 milliseconds or 5 milliseconds, whatever it is. We've never done this one. I've been in telecommunication for more than 30 years. We never designed any network that pay attention as one of the KPIs is the delay. And obviously, the wireless connectivity, everything will be connected through wireless because of that mobility and independence to location. So we need capacity. We need huge amount of capacity. Capacity for low data rate, medium data rate, as well as high data rate. It's not only about broadband communications. And most of the application in future will be based on virtual reality, augmented reality, mixed reality on base 4K, 8K sort of applications. And that is going to get more and more, whether it is for industrial applications or it is for entertainment or whatever it is, most of the application will be based in this sort of type of videos. So we also were told by our partners, industry partners, when you come up with a technique or solution, protocols or algorithm or whatever it is, can you test it to see whether it actually works in an end-to-end system? For this, we set up a test bed on our campus, which is covering 4 kilometers squared. We have 3 macro cells, and we have lots of small cells in order to create dense networks, lots of interference. And that is managed by Operation and Management Center inside the building. Is more than 44 base stations, starting with 4G, LTE, TDD, 2.6 gigahertz, and also connected to Vodafone core network, testnet network, which is about 70 kilometers away from our center. And in parallel, we work on the radio side as well as on the core network side, and being able to compare end-to-end performance of the solutions, whatever technique we want to do. So on the EPC, we summarize the EPC first, and then we realize the problems of EPC for 5G, and then we develop our own core network, which is contributing to standards, which we call it flat distributed core cloud-based architecture. I will mention why is so different from EPC. And this is not, even though most of the radio access was given to us by Huawei, we develop our own core network. So I always say that we develop it. It is vendor agnostic, and is open enough to do any research on the core network, whether it's protocols, whether it's the new routing algorithms, or we can do data analytics on the network, or whatever we want to do. It's completely virtualized and a sliceable architecture. And we tested this one. We can support 1 million users simultaneously on this core network. So some of the aspects of this FDC is, we say that it's efficient, it's flexible, scalable, agile, as well as dynamic in terms of the slicing. I have to see what I've written here myself. And it's somewhat more flat than 4G EPC is. And for example, for 70% of use cases, it goes through one layer of the network, and for remaining 30%, it goes to 2 layers hierarchy of network. So it is good for controlling the latency, and is distributed. Most of the functionality doesn't require on one central point for computing as well as signal processing side, and it is cloud-based. And it is also intelligent. So we have a context-aware networking. And we contributed this one to standards, 3GPP, and it is part of 3GPP, but they don't specify how to implement this context-aware sort of networking side. So we get this protocol, we call it metadata protocol. It collects the information about the user, device status, network status, radio status, as well as core network status, and intelligently will adapt the network in an autonomic manner. And supports true dynamic network slicing. We can set up a slice and virtual networks, logical networks, several logical networks we can set up in a physical network. And a slice from scratch, we can set up one slice in less than 2 minutes. And we can collapse it in less than 2 minutes. And each slice can have its own bandwidth, it's a vertical and horizontal slice. It can have its own dedicated qualitative service or qualitative experience. And so this is one way of managing mixed type of services from all these verticals in one network technology side. Most of this architecture has been contributed to 3GPP standards, either directly from us or through our industrial partners. So that's a quick overview of what we have done in 5G Innovation Center so far. What is next? What are we going to do next after that? Because we are a research organization, so we need to have a way forward to continue our research. So one of my friends, a long-term friend, he used to invent lots of ideas. He was an inventor. And I said to him, how do you come up with these ideas? He says, very simple. Instead of saying what is possible, say to yourself what is not possible. Then you get ideas. So all science fiction films and books have written so far, have been published so far, technically they are implementable. Anything that I can think of. You may say, no, we cannot do teleportation. I gave a TEDx talk in 2015, and it was about future wireless for the next 30 years. And in that one, I said how teleportation can be done. Very top level view, not technical, because the audience were not technical. My wife was sitting in the audience and said to me, oh, you're crazy. So I had to keep it very non-technical side. The reason that many people say it is not possible, because people think about physical body of teleportation. So transporting somebody, the physical body of somebody, and then assembling all the cells and the limbs and hands and et cetera together and make it teleportation. It's not needed to do that. So how it can be done? We have to ask ourselves first, what makes us as a person? Is it our physical body, or is it our conscious? Or is it our 5 senses that we have? Some people have 6 senses, but I'm talking about average people. So it is our senses makes us us. So instead of transmitting a physical body, we need to transmit our senses. And that multi-sensory information needs to be transmitted, but in the right direction, not always from my physical body to somewhere else, but it could be the other way around. So one simple form is, if you want to have experience of this area, you need to transmit somehow all the senses: hearing, seeing, touch, taste, and smell. Transmitting to a person, and we have another receiver that captures all these things from this area, and we feel that we are in that area. So it's not about physical transport, physical body transportation. It's being in a different place and experience different place. And if you want to interact with that location you go to, it could be another body or another entity that would touch different objects in wherever you go and transmit that feelings or seeing, touching, smelling, whatever it is, back to the person. So as you can see, the direction, many people think teleportation is from here to here, but it is mainly from here to here. It's different direction to it. And if you want to interact with the environment, which is cyber world, is not only you transmit essential information, but also you need to retransmit or transmit the actuation, how you react to different smells or to different touch or whatever it is. Therefore, you need to transmit your actuation information. Or instead of that robot, you can transport your holoportation, holographic of yourself with all the senses. And then you can interact with a different cyber world. So holoportation, that can be done with 5G. Let me show you a video that somebody was holoported using 5G 50 kilometers away into my center as a 3D embodiment of somebody. And we were talking to each other in a real time. Let me share that video with you. I hope it works. Sometimes it doesn't. So this guy was holoported about 50 kilometers away from east of London to south of London where we are located. And we were having a chat, sitting there. Obviously, I have to have this HoloLens to see the person, but I'm cheating a little bit, so I'm pretending I'm seeing him. But the message is you can have real-time interactions with anybody remotely. So on top of this, as you can see, the quality is not very good. The quality of video is not very good, but it's a 3D version of that person. So that one, and if you put the sensory information on top of that, that person would be completely in our center. And sometimes two people or more, they would be interacting in real time in a cyber world. So each person will receive the sensory information and provide the actuation in real time between their holoportation with the sensors in a cyber world. Or you can have a social networks of different people, a group of people could be interacting in a cyber world with each other. So the bit rate as you require will be multiple of the bit rate from each person receiving the sensory information, plus holoportation, plus actuation side. So we are technical people, and I stole this one from Richard's presentation. If you want to transmit a high quality of a person in holoportation, a person of this sort of dimension, 6 foot 4 inches by 20 sort of inches, in a high quality one, I think this is a reference, somebody from University of Arizona has done this work. We need about 4.6 terabits per second. Just the holoportation, not the sensing information. So other sensors, again, I talked to my inventor colleague. 20 years ago, he transmitted touch. He built a system, and he transmitted touch. So I wanted to ask him, what sort of bit rate do we need to transmit touch? He said to me, 20 to 50 megabits per second for every square inch. And if it is looking at one hand, probably 1 gigabits per second. With multiple hands, it's multiple of gigabits per second. And the latency, he said, in order to have a natural feel and real-time touch, it has to be less than 1 millisecond. For the brain and the actions to actually interact in a real time. I asked him about taste and smell, he couldn't give me a figure. But it's much lower than this. He said to me, the smell, taste and smell is a chemical reaction. And there's more work needs to be done in this area to quantify what sort of bit rate and speed and latency and etc. is required for this. Audio and visual, we already know what sort of bit rate is required. But the dominant factor seems to be the high quality holoportation side. And uplink and downlink and the sensors is a real-time interactions that requires low latency. So for each person, 4, 5, 6 terabits per second per person. If it is only one person, needs to be holoported. Latency is less than 1 millisecond, but it is more importantly, it is the guaranteed latency side between sensing and actuation, for action and reaction side. Another important thing is because not people are static. Especially when you interact with people, you need to know the relative location with each other. And people reacting in the cyber world. And that geolocation accuracy of 1 centimeter, and more importantly, the location update rate has to be done every millisecond. Every millisecond, it maps to about 30 kilometers per hour. And another important aspect is all these sensors, holoportation, interactions with another person sort of in cyber world, it has to be synchronized with each other. Even if you transmit everything, say 1 millisecond latency, end to end, all this 1 millisecond needs to be synchronized with each other. And that synchronization, some estimation I've done, and talking to my inventor colleagues, seems to be about 10 milliseconds. Synchronization between all this information. So, as a network engineers, we need to say there is no reason for internet in future and a mobile core network to be separate from each other. What should be the starting point to define the new internet? Would it be 5G core as a starting point, or would it be current internet? I think the 5G core has a lot to offer. Well, depends on what is going to be standardized eventually. There's lots of fantastic ideas, context-aware, low latency, flat architecture, virtualization, slicing, whatever it is. But in the researcher community. But what's going to be standardized, we don't know what is going to be eventually standardized. But 5G core is good starting point. But what is not good about mobile networks because of the protocols to be wireless friendly and internet interworking, which is IP, we have lots of tunneling, like GTP tunneling after tunneling of the protocols. And that needs to be taken out. A solution needs to be provided. In our 5G core that we have, flat distributed cloud architecture, it is without any tunneling. You have two versions, actually, one with the tunneling, one without tunneling. So it is possible. And whatever we are going to design, future internet, we have to have mobility and wireless connectivity characteristic in mind. We can't design one network for mobile networks and one for the internet side. From the beginning, whatever is going to be architecture and protocols, we have to have these two important factors, mobility and wireless connectivity in mind, and design the network. Another important thing is, I think it was discussed in Ravi's presentation. I was here just before lunch. The environment is stateful. The internet is stateless. Another important thing is the network doesn't have any memory. I think in his presentation, he said from idle to active state, I can't remember, 21 messages needs to be exchanged. Because we don't keep a memory of what is going to happen, what has happened before. So we start every signaling from scratch again. So the network has to be memoryful, it has to be stateful. It has to have context aware with the intelligence to know the context of the device, a person, and a network. Signaling in the mobile networks, as well as for internet, is the major source of delay, apart from the bandwidth. It's not the UPF, it's not the user plane, it is the signaling. It causes all the delay and repetitive amount of signaling, and most of the signaling architecture is still what we inherited from the GSM 2G, and we built on that. Multiple paths and synchronized path. I mean, as the example we show on holoportation. That needs to be established as part of the protocols. Most of the computing, I think there was some presentation before about the distributed edge computing architecture. Most of the protocols and computing has to be distributed. That provides resilience and minimizes the one point of failure. At the same time, provide computing capabilities. So I suggest we look at distributed ledger technology. Not in the way that it was designed for Bitcoin or crypto coin aspects, but using DLT for more distributed computing and more distributed storage and more distributed signal processing side. The reason I'm suggesting this one, because of the important acyclic graphs in a DLT provide security, resilience, privacy as well. It's very difficult to break into this from any point and reach the endpoint of the graphs. So we need to define different graphs for different functionality, from the application layer to protocols to signal processing side. And when we have that, we already have distributed, not we, as a Surrey University, the distributed, highly accurate time mechanism. And that combined with DLT to do computing in real time, signal processing in real time. At the same time, do a distributed manner. I think that is an interesting research topic to be explored. We don't have a solution, as I said, but it is important to look into that and see what we can do with distributed ledger technology as well as distributed time. Highly accurate. It opens up many, not only from the networking side, but also many, many different applications. On the memory-full networking, we did this work about 5 years ago. We realized, because one aspect of the 4G network, the KPI was, everybody was talking about energy efficiency. We're still talking about energy efficiency, but not as hot as it used to be. So we look at the whole protocols, signaling architecture in 4G and 3G, and so what is the main problem? The main problem we realize, the signaling is repeated over and over, despite the fact the network would know and should know the capability of device. We start everything from scratch. And that contributed quite a lot to waste of energy, the bandwidth, latency. Latency was not a KPI for us at that time. So the network has to have some mechanism to store the historic interactions between a particular device or a person and the network. So we don't need to repeat everything from this scratch. And that mainly, I think it was mentioned in one of the presentations today as well. RRC, for example, radio resource controller. When you want to set up a bearer, the bandwidth of the bearer. All this information is already in the network, but we get rid of that information. Mobility management. There is a pattern in our mobility. We can do predictive mobility if we know the status of a person or a device. And that has implication on the authentication and the speed of authentication of the users. And the user and device context information. All of these are important information that network do not store. Obviously, we have to be careful with the scalability. But there are ways of making the network collecting this information about the user, device, to be scalable at the same time. So there is a huge amount of research in what I've said already, from holoportation with the sensual information, with the actuation, etc., as well as the new paradigm in the networking. That's why when Huawei set up Network 2030, we wholeheartedly supported this aspect, because I was tired of saying that the major innovation for 5G and beyond 5G is in the core network. But 3GPP is a bunch of radio guys that only start radio specification for 5G. So what is next? How we define the next step? I'm reluctant to call it 6G. Right? But that's the way that we have been doing it for the last 30 years. Yeah, 1G, for example, 2G, 3G, 4G. And there was some key performance indicator was identified in order for standards to start working on technical solutions side. So 2G is communication between people. Mobility was important as well. And it was about one of our senses, and that was hearing. 3G, we had the image. So it's a 2D image, not video, plus telephony, obviously mobility and the speed of the data communication, but the added hearing plus video side. 3G, 4G, sorry, talked about capacity, talked about energy efficiency, network, spectral efficiency. These were the main technical justification for 4G. And on top of that, we had hearing plus sight plus time, which is video. So image with time translates into video. 5G has all of this plus new KPIs. We talked about area capacity, not only the physical layer, spectral efficiency, but area capacity, high density ultra-dense sort of network, so it's about area capacity. Guaranteed low delay, that was in 5G. Guaranteed high reliability for Industry 4.0, connecting robots and machines and cars and etc., as well as the mass connectivity, not only just people, but also different things and objects. And that turned the 2D into 3D, like holoportation, which I showed you. Plus sight, plus time, plus mixed reality. So next, how are we going to define it? We'll have all of those plus synchronization, plus geolocation. And that is about, in terms of sensors, I call it 4D. So 3D, if it's holoportation without sensors. So if we have the sensual information there, that will be effectively 4D, or teleportation if you want to call it. And real time, and providing cyber-physical space interactions. So that's the way that the standards identify the standardization. So I tried to put everything in that sort of format. So they would say, what is new? Synchronization. What is new? Geolocation. And what is the applications is that sort of area. As I said, there's a huge amount of work to be done. We don't have the solutions for everything. And like 5G IC, we said that our mission was, what is the art of possibility? I invite everybody, all the good researchers worldwide, to let's identify, without worrying about backward compatibility, what is the state of art? What can we do to make the future internet, or new internet, more fit for purpose for 2030 and above? Thank you.
Futuristic when it's expiring, so to my surprise, no question.
Professor, you talked about combining wireless radio protocols, one network architecture, both mobility and fixed networks. How do you suggest it can be made possible?
Well, the way that we designed, for example, 5G core network has been designed with taking into account the wireless characteristics. So why don't we extend that one to the new internet? So from the beginning, we know, for example, TCP doesn't understand the wireless outage. I think it is congestion, for example. In terms of reliability, on the radio side, from G node B to the device, we can guarantee reliability. From there onwards, we cannot do guarantee reliability because we don't have a dedicated path. For example, for something which is critical in terms of quality of service or quality of experience, so we don't take care of that. And this sort of aspect is not in the internet, but fortunately or unfortunately, all the networks needs to hang from the internet. And the question that we're asking ourselves, can we just carry on designing different cores for mobile core or fixed network or wireless fixed network and et cetera, keep hanging it to the internet? And at the same time, we want guaranteed latency. We want guaranteed quality of service, quality security. For example, security aspects. The mobile networks are traditionally much better in terms of security than internet is. So there are lots of lessons to be learned from both sides, internet as well as the mobile networks. I think what I like about internet is simplicity of its IP layer. IP is extremely simple. Everything you build on top and below that. So can we come up with something similar to that, but it is more wireless and mobile, mobility friendly?
Yeah, I agree with your general principle of trying to evolve towards a mobile internet which is uniform. How do we do that from a standardization perspective? Do you think that 3GPP people will agree to work with IETF and vice versa?
I think this is the battle I had with the GUP. I think there was a WCNC conference in Paris, and the chairman of the 3GP was there, and I had a go. I had a real go at them. And he came to me and said to me, look, we are a bunch of wireless guys. So starting point for us is just a wireless activity. But saying that, 3GPP is changing at the moment. They are more now realizing that the differentiation starts from the core network architecture and the protocols. And they're changing, but not changing fast enough. But they are changing. That is, even the operators, they realize this one. The network operators, they realize this one. The vendors, I mean, we work very closely with Huawei, but there are very few vendors who are very progressive, and they realize the world is going to be different from in 20, 30 years' time. So they are adopting and putting more emphasis on the core network side as well. So we shouldn't give up, right? We should just carry on and work and promote our area and say what can be done if we come up with the new protocols. We have to tell the industry and the stakeholders what is the art of possibility. That's what we need to do.
So thank you for the talk. So you said we cannot guarantee latency. We only can have a probability that the latency is inside or up to a maximum bound or something else. So do you see in future some new opportunities to have a real guaranteed low latency?
In mobile core network, we guarantee latency. We have URLC as part of our testbed. We have the radio and it's connected to our core. It's a form of like a standalone core. We can establish end-to-end latency 99.999% of the time. So it is possible. But when it goes to internet, you cannot do that. And I don't know, Richard, you are chairing this session. I have a video of controlling a robot on a two-wheel using 4G and using 5G URLC. And you see the stark differences between the two if the delay is not guaranteed. I don't know, but do you want me to show that? Or
yeah, feel free if you
no.
have it.
I have it.
Okay.
into our lab, into our canteen to show that one. So it is connected. We have a CPE UE from Vodafone, which is wired connected to the robot. But that CPE connected wirelessly URLC to the base station, and it's connected to our core network.
So when you say URLC, you are basically using the 5G aspect.
Yes, yes. But URLC is not finalized, the standard, but so we call it pre-5G standards.
Guarantee requires additional control. If you have 100 people trying to do the same thing on a small
Yeah.
network, it's never going to be.
Yeah. I think one of the problems, the research problems with URLC is spectrally efficient is very low because the spectral efficiency has been sacrificed for the latency, guaranteed latency. So the research that my team is working on to make it more spectrally efficient as well. Yeah. Hmm? Yeah, but when you set up a call to a robot, the delay is not important. When you have already set up the bearer, after that, you need to guarantee the delay because you keep sending commands back and forth between network and the robot.
So with the connection-oriented protocol, AKM was an example of something that
Yeah.
end-to-end, but the efficiency was a problem.
Yeah, that's right. Yeah. Good old ATM.
So in the old days, with voice and video, we used to make the case that we needed low latency, very tight jitter. And over time, we sort of adapted the applications to be able to tolerate latency jitter. If I look at, these new approaches for networked capabilities with robots, the control loop that they're used to having is still the traditional electronics approach. Is there a need to rethink those applications as well when you go out to making it, distributed?
Protocols and algorithms, whatever is going to, we need to have these KPIs in mind, of course. This jitter in delay, for example, to some extent, maybe say 99.999, that means about 10 to the power minus 5. So that is acceptable. Depends on the application side. But like 4G, you see the delay varying. If the delay, for example, for a robot, for guaranteed 50 milliseconds, and if we guarantee that one, then we can expect this 50 millisecond delay. And then we can have reliable communication. But we cannot, robots cannot tolerate jitter in the delays, for example. I mean, we talk about video, this is subjective quality. Unfortunately, robots are not, fortunately, probably, they're not like human beings to tolerate that sort of jitter. They are robots and they are electronics, and they expect the commands to receive within a certain delay and reliably. So it's the same problem. I think it requires a different solution because it's not about human beings sitting at the end of that. Most of the things that quality of experience needs to be re-engineered again.
So regarding this sensing delay, I have some question. Usually we assume that if the delay is less than 150 milliseconds, this is okay for a human being. For instance, for interactive communications, video conferencing, Skype calls or something else. If the delay is less than 150 milliseconds, it's not a problem for a human being. So we are not able to sense better than 150 milliseconds. So in your talk, you assumed that it's 1 milliseconds for some senses. So is it? Where do you have these figures, or is it really so tough, or can we also rely on this 150 milliseconds? This is my question.
Video conferencing, yes, the delay up to 400 milliseconds is okay. And people understand that. Wait until you hear the question, and then you respond, and etc. That's, for example, if you see BBC talking to a reporter other side of the world, there's always satellite delay. And I think the audience understand that. They wait, they know there's nothing wrong if both sides are quiet and silent, because they know there is a delay side. And talking about these sort of figures I mentioned, if you look at virtual reality games, virtual reality gaming, if the delay is more than 10 milliseconds, you feel dizzy. No, we have the virtual reality in our center. You get dizzy. You get this dizziness. It's less than 10 milliseconds. So when we are talking about holoportation and real time touching, and sorry to touch you, etc., it has to feel natural. So that's what I don't know about the figures, but I talked to my friends that would work in this area, and they said for that natural feelings and natural interactions with the cyber and the physical world, and etc., that sort of delay is required. I think it was in your presentation. You said, was it your presentation? It was about, I think you had 8 milliseconds. Yeah, 8 milliseconds. So, for example, yeah, if you want to control an electricity network, 8 milliseconds is too long. 1 millisecond. I think that is the most strictest delay that you can see in the application of the 5G to Industry 4.0. 1 millisecond. For VR sort of gaming and etc., less than 10 milliseconds is, they say, this sort of acceptable to users.
Yeah, sorry, I have to cut off here. We have a time issue, so let's thank Rahim give us interesting talks. But he will stay here for a few more hours.
Thank you. Okay, so we are gonna start the third and last session with technical papers, and we're gonna talk about Dataplane innovations, starting with Georg von Zengen. I hope it's kind of cool. Thank you. From TU Braunschweig, who's gonna talk about AIRCON-Stack.
Hello. Maybe it's working. Actually, I feel like I have a bit out of scope here because, I'm coming from wireless sensor networks, IoT stuff, basically. So keep that in mind while my presentation. Things might be different here. So what it's about today, introducing flexibility into wireless industrial real-time networks. So these huge networks which are controlling some manufacturing facilities. So what is it nowadays? They are not flexible. You build a manufacturing plant and then you run it hopefully for 10 years without any changes. Or slightly changes. And if you look at research in that topic, it's mostly focusing on getting the delay as low as possible, so you have faster feedback from your machinery, and also in other network disciplines. It is more on delay or bandwidth, actually. But actually, the jitter, so the variant of the delay we heard just for the video, it was great. Thanks for the video again with the robot. It was a nice one. Yeah, because if you have closed loop controllers, your delay has to be quite constant. As we have seen, if you have a variety in your delay, it was. So, yeah, that's one of the advertisings here. Look at the jitter in your networks. It will be even more important in the future. Because when I talked to some manufacturing planning researchers, they had some ideas about how does future plants look like. They say they will be much more flexible, so you won't build a plant that's producing things for a long time the same thing, so you have to change it more frequently. And actually they want to have wireless connections in there for controlling their plants and machinery. And the problem is that rewiring these machinery is quite expensive. So they want to have wireless connections here. And in far future, they plan to have like mobile robots that are somehow cooperating. So you have two robot arms on wheels, which are carrying some pieces together. So they have to have really good real-time networks so they don't break your piece to work on. So what do we focus on? Yeah, we try to build some networks that can introduce this flexibility so we can change the network during operation. And we focus on reducing the jitter. What do I mean by flexibility? Well, we want to change the topology. Yeah, so we have one machinery in one point of the plant, and now we want to change it and put another one next to it, and there's some wireless communication in both of these machineries. But we don't want to stop the manufacturing line, which is already there during the build of the other one. So, yeah, talking to people who do closed loop controllers, yeah, they say they don't see, and we don't see anything different than some sort of TDMA to have real-time capabilities in networks. So we use them. And yeah, flexibility means somehow changing these TDMA schedules without disrupting real-time applications that are already running in the networks. Yeah, and they have to have some sort of scheduler that calculates schedules so both machines can run in the end, and we don't have to stop the one machine that is already running. Yeah, here a disclaimer slide I put in, just, you know, I'm not having like huge racks of base stations for thousands and millions of dollars. My hardware is quite low cost. It's more in the hundreds of kilobit per second range than gigabit per second range. And I work on CPUs with hundreds of megahertz, not gigahertz. So it's a little different, as I told you at the start. Yeah. Okay, so let's get to the system I am actually presenting. Can't see my clock. Ah, there it is. Okay. Yeah, so the system architecture is pretty basic. In the middle we have a network stack. We already presented last year our clock synchronization. It's microsecond clock synchronization, so it's quite accurate for the network. What I'm going to present here is the task and radio scheduler. So we're using a scheduling that is basically, joint scheduling. So because people often ask, why do you have to schedule this at one thing and don't schedule tasks and your wireless transmissions differently? Well, if you want to control the jitter of a measurement that is somehow delivered to another network node, you also have to schedule the taking of the measurement and not only the transmission of the measurement. So therefore, it's just a joint scheduler, so we don't have to concern about this 2 times. Yeah. On top of it, as always, there are applications that are somehow using our network stacks. And just below there is a physical layer, an ultra-wideband, to have less interference from microwaves, Bluetooth, Wi-Fi, and stuff like that. Yeah, so how do we partition time? I've drawn here 2 lines actually. One is the CPU, which is the upper one here, and then I have called it the AIR schedule, which is just transmissions. And here we see that over here it's just a task, so it's CPU task 0 and then following a CPU task 1. And what we do is we have like here, the red one is the worst case runtime. So if a slot starts, we wait until the worst. We have left the worst case runtime, and we start the schedule, the task. And at the end of the CPU slot, we immediately start the transmission slot, and we transmit the data. So we can somehow say that, the scheduling is going quite a little bit diagonal in this graph here. So, and due to the capabilities of our ultra-wideband radios, we can load the data which we want to transmit directly to the radio, and the radio then will transmit at the exact time we want it to transmit, so we don't have to use the CPU as in normal wireless sensor networks to transmit the packet. It's done automatically. So partition of time 2. It's an in-depth view of our slots for the CPU. We get an interrupt basically where we start our really simple scheduler that just says, okay, which task do I have to start now, and when do I have to start it? So that then sets the next interrupt and fires up the task at the worst case runtime. So we can make sure that there is very low jitter in here. That is somehow the jitter which is there because we have a worst case runtime and we not always use the worst case runtime. So, okay. Then we did a little tiny evaluation. For that, we took a really small network of 4 nodes connected them all to a logic analyzer, took a GPIO from our CPUs and connected it. And yeah, basically what we do is we take the master to tell the slave that it should just toggle its GPIO pin in the next frame of slots. And yeah, these are 4-time synchronization, which are obviously needed. So how do these results look like? As a baseline, we have just one schedule, no changes, no nothing. What you see here is not the actual delay. It's a delay minus the time between the slots. Because otherwise, the slot is like 10 milliseconds long, and if we'll want to draw something which is a delay of 10 milliseconds and then try to see to microseconds, it's quite hard. So we remove that. Yeah, as you can see, all of the nodes are somewhere in the 2 microsecond range of delay variation here. And as I said, we want to have a little bit of flexibility in our network. So we started changing schedules. Yeah, they are quite similar, I know, but it makes it easier to compare. So by changing schedules, we introduce a little bit of jitter because we have the master to tell the slave when to change the schedule, then they change the schedule, and that sometimes glitches a little bit. Therefore, we have a little higher delay here, which is in the 4 microseconds. Okay, to conclude my talk already, I've made it a little faster so we can get coffee. Yeah, so we have a low jitter optimized system. In here, we have the ability to handle changes in the scheduling without introducing too much new jitter. Yeah, we are below jitter of 6 microseconds under all conditions. Yeah, we have some future work to do, actually, scheduling real tasks with changes of tasks. So we have to have some scheduler that respects jitter bounds for our network system here. Yeah, and with this, I'm already done. I thank you for your attention, and if you have any questions, just ask them at the coffee break. I don't know.
Thank you. Thank you, speaker. So we have time for a couple of questions, if there's any. Yes.
You have a dedicated task for that. The CPU is doing a single task periodically, right? Why did you need to do interrupts? You could just poll.
Well, the CPU has not just a single task, it also has tasks like preparing packets, and the idea is that we put a lot of tasks to the CPU. So yeah, we tried polling first to have low delay, but actually there was a lot of jitter in it, and the interrupt was just better. So we used, and we could spare some CPU cycles.
other question? Sure.
So you mentioned that the jitter is important, right? What about the delay? Because I think from my point of view, first we should deal about the delay, and then the jitter is related to the delay, right? And you didn't speak so much about the delay. What are your requirements, and how is it, in your case, delay and jitter related to each other?
Well, in my case, it's the variance of the delay is a jitter. So, yeah, I mean, in control theory, you can handle some sort of delay in most systems. Not in these human systems, but, or in, yeah. Well, because in normal controllers, you can say my my value is of that age, so I can estimate how far I went with the value by now. If that is changing a lot, parameterizing these controllers gets harder. That's so far I understand the guys from control theory. So they said we can handle a certain delay, but we are not happy with the jitters.
Okay, we have time for a very quick one. If there's any, I have one curiosity. In slide 5, you said that your background relates more to the low power hardware. Is that a design choice or a constraint given the environment that you're working in?
Well, actually, it's more like my personal background is I'm a guy from wireless sensor networks, and yeah, that's, I mean, maybe you can throw a lot of money to it and have very centralized networks, then things are working, I guess, better. But if you want to do it low cost, because yeah, if you sell machinery to people, they also look at the money. And yeah, saying them, oh yeah, first have to spend, I don't know, 2 million for our network, and then you can buy a machinery that works. They maybe not that lucky.
A good idea for a future comparison. Okay, this is the half time. This session is actually split in two. We are about 10 minutes late, so I ask you to cut the break short, about 10 minutes. So I'll see you back in about 20 minutes, and we start again. And there will be the panel after the second half. Thank you.